Hello, this is Addison and I's final project for multivariable calculus on the Fourier series and the Fourier transform. So what exactly are the Fourier series and the Fourier transform? The Fourier series is a mathematical technique used to represent a periodic function as an infinite sum of simple sine and cosine waves with varying amplitudes, frequencies, and phases. By breaking a function down, we can study the behavior of complex periodic functions in simpler terms of simpler components, and gain insight into its underlying structure. The Fourier transform is a mathematical tool used to transform a signal from the time domain to the frequency domain, allowing us to analyze the signal in terms of its frequency components. By breaking down a signal into its constituent frequency components, we can gain insight into its spectral content, identify hidden patterns and trends, and even filter out unwanted noise or interference. The Fourier series and Fourier transform are related as they both deal with the analysis and representation of signals in terms of their frequency components. The Fourier series represents periodic signals in terms of a sum of sinusoidal waves, while the Fourier transform represents non-periodic signals as a continuous spectrum of frequency components. The Fourier transform can be viewed as the limiting case of the Fourier series as the period of the signal approaches infinity. Together, the Fourier series and Fourier transform provide a powerful mathematical framework for analyzing and understanding signals in a variety of fields, from music and sound analysis to quantum mechanics. The Fourier series is named in honor of Jean-Baptiste Joseph Fourier. Fourier introduced the series for the purpose of solving the heat equation in a metal plate, publishing his initial results in his 1807 memoir, sorry I don't speak French, but Memoir sur la propagation de la chaleur dans les corps solides, or the treatise on the propagation of heat in solid bodies, and publishing his Theorie analytique de la chaleur, or Analytical Theory of Heat, 15 years later. The memoir introduced Fourier analysis, specifically Fourier series. Prior to Fourier's work, no solution to the heat equation was known in the general case, although particular solutions were known if the heat source behaved in a simple way, in particular if the heat source was a sine or cosine wave. These simple solutions are now sometimes called eigensolutions. Fourier's idea was to model a complicated heat source as a superposition or linear combination of simple sine and cosine waves, and to write the solution as a superposition of the corresponding eigensolutions. This superposition or linear combination is called the Fourier series. Fun fact, he took a prominent part in his own district in promoting the French Revolution, serving on the local revolutionary committee, and was briefly arrested during the Terror. Additionally, Fourier accompanied Napoleon on his Egyptian expedition in 1798 as a scientific advisor, and was appointed secretary of the Institut d'Egypte. Cut off from France by the British fleet, he organized the workshops on which the French army had to rely for their munitions of war.
So now that we have gone through an overview of what the Fourier series and transform are, we're going to go through a derivation to understand the origin of these two principles and their respective formulas. So first we're going to run through the series, and then we're going to convert this series into the transform. So first, the underlying principle that makes the Fourier series work is the concept of orthogonality, which essentially states that if you take the inner product of two sinusoidal waves with differing frequencies, you're going to get a zero integral, and if the frequencies are equal, you're going to get a non-zero integral. So first we're going to show this. You can see here we have two sinusoidal waves of differing frequencies, and then we're taking the inner product of those two waves. So first we're just going to do a product rule trig substitution, then we're going to integrate. Then you can see there's two possible states, one of which you have m is not equal to n, the other you have m equals to n. If m is not equal to n, the above is just going to evaluate to 0 because you have integer multiples of sine pi, which just equals 0. And so this will obviously just be 0. However, if you have m equals n, we're going to come back up here, substitute n for m, and then simplify, and we're going to arrive at this. Then we integrate, and then we simplify, and we find L. So we can see here that if we take the inner product of two sine waves with an equal frequency, we get 0, and if they're equal frequency, we get L, and if they're differing frequency, we get 0. So thus we have this principle here. This little operator is a lemma where you have 1 if m equals n, 0 otherwise. So this is just a nice way to describe this principle of orthogonality. And so following the exact same logic as above, we just apply this exact same methodology to the cosine variant, and we get the exact same thing as with sine. Then we can actually have orthogonality with sine and cosine. Sine and cosine are always orthogonal because if you multiply an even function by an odd function, since the bounds are symmetrical, you get an even function, and the integral over an even bound of an even function is 0. So now that we've demonstrated this principle of orthogonality, we're going to use this to find the Fourier coefficients. So first, we have a function f of x that is 2L periodic, and obviously since we're doing the Fourier series, we're going to assume it can take the form of an infinite series of sinusoids, as we have here. Each sinusoid of a respective frequency n has a coefficient a of n and b of n to go along with it. And since at n equals 0, there's no b coefficient, we're going to do a reindex just to simplify things. And then we put a 1/2 in front of the ace of 0 just to make things simpler down the road. So we just reindex the series as such. Then we're going to integrate both sides, negative L to L. It's pretty straightforward here. This is just a straightforward integration over here. And since, as we said before, when n equals 0, sine is also 0, so this guy just goes away, that becomes 0, and then we integrate, and we have this guy. And then we plug in 0 for n. And then this is how we get ace of 0. So now that we have ace of 0, let's find how we're going to figure out the rest of the coefficients. So we reintegrate what we just had up here above, except we're going to multiply both sides by cosine m pi of x over L. And then this is where the principle of orthogonality comes in again, where we're going to use it. So this is just an even function, so this integral guy over here becomes 0. This guy over here becomes 0 by the principle of orthogonality. And then this guy is going to equal L a of n lemma m of n, just by the orthogonality principles that we demonstrated above. And so this is going to equal 0 anytime m is not equal to n. So in order for this to equal something that's non-zero, n is going to have to equal m. Thus, this will just simplify to a of m, and then we divide both sides by L. And so this is just a nice, simple definition of how we're going to find the a of m coefficient. And this is really like a really intricate function, yet it's also very simple at the same time. Like we're just taking, if we want to get the coefficient for the sinusoidal wave of a given frequency m, we just integrate the inner product of the original function with that sinusoidal wave, which is really simple, but we'll get to the intuition later, as this kind of on its own doesn't really make a lot of sense, at least it didn't to me when first going through this. So we're going to repeat this same process again, except multiplying both sides by sine m pi of x, and we use the exact same orthogonality principles as before to find the definition of the b coefficient. And so this is the Fourier series, and then this is how you derive the coefficients for the Fourier series. And that is pretty much all there is to the Fourier series. It's relatively straightforward, and ultimately ends up being pretty simple, but the reasoning why this works is not as so clear, which we'll get into in a bit. But before we do that, we're going to derive the Fourier transform. And we're going to do this by just converting the Fourier series into complex form, and then converting the complex form into the Fourier series. And so really the Fourier series is ultimately just the Fourier transform, is ultimately just the Fourier series, but over negative infinity to infinity and integrating over every single frequency there is. And so it'll become very clear at the end how the two are related, and they're ultimately really similar. So by Euler's formula, we have a definition of cosine and sine using complex exponentials. So we have the original definition of the Fourier series. We substitute in our new definition, or our just definition that we have here of cosine and sine. We do this a few times, and then we simplify. And then here we get to the slightly tricky part. Excuse me. We re-index the n to be negative n so that we can flip this guy around. And then what we do is we change this coefficient to be described as c of n, just so it's a little bit cleaner and simpler. And then we can combine this sigma and this guy into 1, from negative infinity to infinity. And this is the complex Fourier series. So now that we have this, we can just plug this definition of c of n back into the Fourier coefficients formula that we outlined previously to find this. And so now we have the Fourier series in complex form along with the coefficients in complex form. So now that we have this, we're going to evaluate the Fourier series from negative infinity to infinity, and then see what happens. So first we have k of n equals pi n over L. This is just as we saw before, it's in the integral, it determines like which frequency of sinusoidal wave it is. And then we're going to define delta k, which is essentially just the increment to the next wave count, because this is just a new increment. When you increase n by 1, you're essentially just adding pi over L to k over n. So then we're just going to rewrite the Fourier coefficient that we found up here as a function f of b. And then we have c of n, and we're just putting in this big F into our definition of c of n. And then we substitute into our new definition of the Fourier series this big F. And then we get 1 over 2L equals delta k over 2 pi, which is just a depot based on this, dividing by pi and then divide by 2. And so it's a little unclear why we might have done this, but now we're going to substitute this delta k into this guy over here with the 1 over 2L. And so this might look really familiar. We have a little delta k here. We have an infinite sum. And so this is actually a Riemann sum. And so every little increment of x along the x-axis is a new frequency, which is what delta k is. So we can convert this into an integral, and boom, we have the Fourier transform. So essentially what you can do here is you plug in some frequency x, and then this integrates over the coefficient to find its amplitude in whatever function you're trying to find, and then it'll plot you a nice Fourier transform. So that is the derivation of the Fourier series, and then I'll run through some intuition for how these things actually work and why they work, and how the orthogonality fits into it. So now let's get into some intuition and understanding of how the Fourier series works, and how the transform works, and how orthogonality fits into all of that. So first, we have a little slider here. We can see we have two parameters. One is the length of the period, and then 2 is the length of the Fourier series. As you can see, as we decrease the length of the Fourier series, our little approximation becomes not very accurate, and then as we increase the counts, it becomes more and more accurate. It takes a little while to load. I did my own implementation of it just to make sure I understood it, but I think it's much slower than how Mathematica does it. And then we can increase the period as well. So it's pretty straightforward. We have a very good Fourier series here of just y equals x. We have 50 terms in the series. And then here we have a Fourier transform of a line. We can see that it's pretty similar to the coefficients. I'm not exactly sure how the coefficients relate to the Fourier transform. The shape is the same, but the values are not exactly the same. So that's something I need to dig into further. You can see here they're superimposed, and you can see they're quite similar. So now let's understand how the orthogonality principle applies to sine and cosine. So you can see here on this plot, we have two cosine waves multiplied by each other of frequency u and z respectively, and we have sliders here to manipulate that. So first, we'll start here at 1. So let's actually bump you up to 3. So we can see here as we increase the or change the frequency, we can see here that the area, the integral of these two waves multiplied by each other over a very long period is very small. And this is expected. This is like the orthogonality principle that we determined in the derivation. You can see no matter what we do, the number is still like basically 0. However, as we get closer and closer, the area becomes very large. And so this is where the waves are equal. And so when the waves are equal, if you take the integral from negative infinity to infinity, the area is going to be infinity because the waves become only positive. They reinforce each other at the right spots and they become only positive. And then as soon as you change it, they become, you can see here 5, it's still, a decent area. But then as you move away, the area gets smaller and smaller again until it goes back to basically 0. So how this relates specifically to the Fourier series is with every wave, you're incrementing the series by 1. So you can see here, it's basically taking the integral of some function multiplied by cosine or sine of some frequency, and then that basically gives you the coefficient. So let's say we're trying to get the Fourier series of cosine of 3x. You can see here, if we for n equals 1, the coefficient is going to be basically 0. If we go to 2, coefficient's basically going to be 0. But if we go to 3, which is the frequency of which the function we're trying to get, we get a very large number. And so we're going to get a decently sized coefficient for that value. And then as we increase it, it goes back to 0. And so basically this notion of orthogonality is why the Fourier series is able to work, because within every single function, there is some, like I like to call it, like a resonant cosine wave, where if you match up with the correct, if you take the inner product of a cosine wave that is like one of the resonant cosine waves within that function that you're trying to approximate, you're going to get a very large area and the coefficient is going to be larger. So that's kind of the intuition for why orthogonality is useful. So now let's get into the Fourier transform, a little bit of explanation of how that works. So first, if we take the Fourier transform of cosine x, we're going to use cosine x again because that's what we used up here, but if you take the Fourier transform of that over negative infinity to infinity, you get this. And Dirac delta is basically a function that gives you infinity at 0 and then 0 everywhere else. And the reason why this is because from negative infinity to infinity, you can get a perfect Fourier transform. So you know exactly like what the frequency is. However, say we go here, we have a piecewise function. It's just cosine x from negative 100 to 100 and then 0 everywhere else. And then we perform the Fourier transform of that. We get a less perfect Fourier transform. The Fourier transform of the perfect cosine of x would have just been a point here at 1 at infinity and then 0 everywhere else. But we don't get that because it's over not an infinite range. And then we can see here, if we take the Fourier transform over a longer range, we get a more perfect Fourier transform. It's tighter, it's taller, and so this is how that works. It took me a really long time actually to figure out these Dirac deltas. I was like really confused, and then I realized that it's because I'm taking it over an infinite range, and then you take the Fourier transform over a shorter range because that's the intended use of the Fourier transform. So now we take the Fourier transform of cosine x plus cosine 2x plus cosine 3x, and you can see here we get a spike at 1, we get a spike at 2, and we get a spike at 3. And this makes sense because as you're integrating for this Fourier transform, you're integrating this multiplied by like cosine, I don't know, call it 0.5 of x right there, And because that wave is orthogonal to these other cosine waves, the frequencies don't match, you're going to get something that's zero, or pretty close to it. And so you get 0, 0, 0, 0, boom. And then when you get to 1, the inner product of this and cosine 1 of x is 0, and the inner product of this and cosine x is 0, but the inner product of this and cosine x is non-zero. And so that's why you get a spike there. And then the similar principle applies for why you get the spike at 2 and 3. And this exact same principle of like linearity of integrals is how this works when you expand this to more complex functions, where because of the original definition of a Fourier series, you can split up any function into an infinite series of cosine and sine waves. And because of the linear properties of integrals, when you take the inner product, you can split that up into every single sinusoidal wave of the original function, and all of the ones that do not have an equal frequency to the sinusoidal wave you're taking the inner product of will equal 0, and the ones that match are going to have a very high area, and so they'll like kind of become resonant in that sense. And so that's why orthogonality is very useful, and how this actually works with a little bit of intuition for the ultimately really simple formula, which is just 1 over L integral over the period times function of, or whatever function times your cosine of the nth value in the series. So that's exactly why that works.
Now we'll move on to some of its applications. The heat equation, first developed by Joseph Fourier in 1822, is a mathematical description of how heat is transferred in a medium over time. It is a partial differential equation that relates the temperature distribution in a material to its thermal properties and the rate at which heat is being generated or absorbed. In the context of the heat equation, the Fourier transform is applied to the temperature distribution to obtain its frequency spectrum. By decomposing the temperature function into its constituent frequency components, we can better understand how the heat is being transferred over the material over time. This approach is particularly useful in problems that involve periodic or symmetric geometries, where the temperature distribution can be easily expressed as a sum of sinusoidal functions. As the prototypical parabolic partial differential equation, the heat equation is among the most widely studied topics in pure math. Its analysis is fundamental to the broader field of partial differential equations. Another application of the Fourier series is sound analysis. Sound analysis is the process of analyzing sound signals to obtain information about their characteristics, such as frequency content, amplitude, and time domain properties. Sound signals are typically analyzed using mathematical tools such as Fourier transforms, which allow us to compose a complex sound signal into its constituent frequencies. Hardware analyzers have been the primary means of signal analysis since the invention of the first audio analyzer. Hardware analyzers are typically used in engineering, testing, and manufacturing professional and consumer-grade products. However, as computer technology has progressed, integrated software has been introduced, and audio analysis no longer requires auxiliary hardware components. Instead, software audio analyzers are now regularly used in various stages of music production, such as live audio, mixing, and mastering. This software often uses the fast Fourier transform, and in using it, we can obtain a frequency spectrum of a sound signal, which represents the energy of the signal at each frequency. This allows us to identify the frequency components that make up the sound and measure their amplitudes, which can in turn provide information about the characteristics of the sound, such as its pitch, timbre, and intensity. Moreover, the Fourier transform also enables us to perform filtering and manipulation of sound signals in the frequency domain, which can be useful for noise reduction, compression, and other signal processing applications. Next, quantum computing. Quantum computing is one application that is made popular by the quantum Fourier transform, which is a linear transformation on quantum bits, and the quantum analog of the discrete Fourier transform, which is a linear transformation on quantum bits. The quantum Fourier transform operates on quantum states, which are superpositions of different basis states. These quantum states are represented by complex numbers called probability amplitudes. These amplitudes can be positive, negative, or even complex, instead of non-negative numbers between 0 and 1. Quantum states allow decryption to happen much faster, just as the traditional Fourier transform decomposes a function into its constituent frequencies. The quantum Fourier transform decomposes a quantum state into its constituent basis states. The quantum Fourier transform is a fundamental building block of many quantum algorithms, including Shor's algorithm for factoring large numbers, a key component of quantum computing. Quantum computing would allow most complex encryption to be broken down, and, as a result, US Congress has passed legislation mandating that all government agencies transition to new methods of cryptography, as some nation-states have already begun accumulating encrypted data to be de-encrypted later on. Lastly, we have Heisenberg uncertainty. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that states that it is impossible to precisely know both the position and momentum of a small enough particle at the same time. More specifically, the principle states that the product of the uncertainties in a position and momentum cannot be less than a certain value, which is a constant value known as Planck's constant. The Fourier transform plays a critical role in explaining the Heisenberg uncertainty principle because it shows that there is a fundamental trade-off between the precision with which we can measure the position of a particle and the precision with which we can measure its momentum. Specifically, if we measure the position of a particle with high precision, then the Fourier transform of the wave function describing the particle will have a wide spread of momenta, indicating a high degree of uncertainty in the momentum. Conversely, if we measure the momentum of a particle with high precision, then the Fourier transform of the wave function will have a wide spread of positions, indicating a high degree of uncertainty in the position.
So, now that Harris has explained to you what the Heisenberg uncertainty principle is, we can have some intuition for why this uncertainty principle happens. So if you recall before, these Dirac deltas, when we took the Fourier transform over an infinite time, a very long wave, we got like a perfect Fourier transform, an exact point at 1. But when we took the Fourier transform over a shorter range, we got a less perfect Fourier transform. And this exact principle is why we have the Heisenberg uncertainty principle. If the original function is narrow, we're going to get a lower magnitude / less tight Fourier transform. But if the original f function is very wide, we're going to get a pretty good tight Fourier transform. And so very simply put, if you're very wide in the time dimension of your original function, you'll be narrow in the frequency dimension. And if you're wide in the frequency dimension, you're going to be narrow in the time dimension. And intuitively, this makes sense because time is measured in seconds and hertz is in 1/seconds. And so these two values are inversely related. But also, say you clap, for example. It's going to be really easy to tell when in time that clap took place, but it's going to be really difficult to tell what the frequency of that clap was. Whereas if you were going to sing a note for a really long period of time, you could know what the frequency is, but you don't exactly know when in time that happened. And so this exact principle is analogous to quantum mechanics and the wave function. So this kind of clap and sound is analogous to position and momentum. So according to de Broglie's hypothesis, which is P equals Planck's constant over the wavelength, it essentially relates position to momentum. This is a theorem I don't really understand outside of the formula and how it relates to this, but that is kind of what relates momentum and position of wave functions of particles. But if we come down here, we can see we have two different wave functions. This is just like particle in a box. Pretty straightforward. We have blue, less certain, it's a bigger box, we don't know where. We have a less certain idea of where the particle is, between -1 and 1, whereas we have the orange guy, which is between -0.5 and 5. And then we take the Fourier transform, which is de Broglie's hypothesis, to get the momentum. And you can see here, with orange, we had a tighter wave function, so we have a better idea of where it is, but we have a less good idea of what its momentum is, as you can see by its much wider probability distribution of its momentum. And then you can see the blue, which we have less idea of where its position is. We have a much narrower probability distribution for its momenta. So we have a little box here On the left, we have a solution to the time-dependent Schrodinger equation. On the right, we have the Fourier transform of the solution of the time-dependent Schrodinger equation. Here we have position on x-axis, probability on the y. Here we have momentum on x and probability on y. So you can see here, as I increase the width of the box, i.e. we're decreasing the certainty at which we know where the particle is, we are actually getting a better idea of what the momentum of the particle is. This distribution is decreasing in width. This is Heisenberg's uncertainty principle. We have our uncertainty of position is increasing, but our certainty of momentum is increasing. And you can see the contrary. So as we are lowering the increasing the certainty at which we know where the particle is, we're increasing the uncertainty of momentum, as you can see by the wide probability distribution on the right. So this is pretty interesting, and it's a fundamental component of the Fourier transform. As we saw intuitively over here, with taking an infinite Fourier transform and getting like a Dirac delta, which is just 1 point at infinity, and then taking a piecewise and getting a less perfect Fourier transform. And so that serves as the intuition for Heisenberg's uncertainty principle and how the Fourier transform helps explain that in an intuitive sense.